Thank you very much for introduction. I'll start my presentation in the following title. I'm Suguru Endo from NTT, working on quantum error mitigation and the divide and conquer technique for NISC and early fault tolerance quantum computing. Okay, and long story short, the current status of the quantum devices is like quantum computers are quite noisy. Quite noisy, so we need to suppress errors, so we need to have quantum error mitigation. And also another problem is like the number of the qubits is not enough. We cannot scale the quantum computers fully, so we need to have divide and conquer technique, which is like we divide and conquer outcomes of multiple quantum processes to simulate the outcome of larger quantum devices. I'll explain about this more. So quantum error mitigation post-processes outcomes of quantum computers, noisy quantum computers, to estimate the noise-free expectation values. So suppose that we have the quantum computer with some error rate, epsilon 0, and we measure the expectation value corresponding to this error rate. And even when we cannot reduce the error, we can boost the error with some technique. So we have another expectation value corresponding to the larger error rate. So we have more plot here. And by extrapolating these 2 points with linear or polynomial or exponential, we can infer the estimates the ideal expectation value. This is called the extrapolation technique. And the important point is like we individually measure the noisy quantum computers with different error rates, and we obtain the expectation value, and the classical computer post-processes these outcomes to estimate the ideal value. And the divide and conquer technique can be understood in this way as well. So divide and conquer technique is like we have the small system A and system B, perhaps system C, system D as well. And we measure the outcome from system A, and we measure the outcome from system B, and we measure the expectation values, and we send this to the classical computer. And again, classical computer tried to emulate the entanglement between system A and system B with classical post-processing. And in this way, we can simulate a larger composite system A plus B. Okay. And this is overview of the talk. I'll talk about both the divide and conquer technique and the quantum error mitigation. And the basic idea derived from the very important quantum algorithm, quantum subspace expansion, which is also abbreviated QSE. And one evolution path is like, so we evolve the quantum subspace expansion to divide and conquer method. And the very general algorithms for divide and conquer technique is formulated called hybrid tensor network, HTN. And our work is like, we developed this hybrid tensor network so that we can compute the transition amplitudes in hybrid tensor network. And actually, the noise is also a very important aspect of quantum computers. So we incorporated the effect of noise in hybrid tensor network, and we had the noise analysis. And the other avenue is quantum error mitigation. By proposing the very general formulation of the quantum subspace expansion named generalized quantum subspace expansion, we propose a very high-quality quantum error mitigation technique. But this has a large overhead using the copy of the quantum states. So we also develop this method so that we can perform error mitigation in a resource-efficient way by using the dual-state purification technique. And finally, by incorporating the essence of the divide and conquer, we propose a divide and conquer dual GST technique, which can simulate a larger system as well as mitigating errors. Okay, then I'd like to talk about quantum subspace expansion. This is a basic hybrid quantum classical algorithm. Suppose the situation we are very interested in the ground state of the Hamiltonian as in the convention of VQE. And suppose this is an approximation of the ground state. But suppose the case we are more interested in a higher quality ground state which has a lower energy. And to do this, we try to apply some projector-like operator, which is decomposed as a linear combination of the Pauli operators. And this CI is a classical parameter we'd like to optimize to lower the energy. And by applying this projector-like operator, what we obtain is like this psi QSE state. This is a hybrid quantum classical ansatz state. And this is expanded like this by applying this one. And by defining the product of this Pauli operator Pi and the original state psi, we define this quantum state psi I. And we can realize the superposition of the linear combination of this quantum state with classical parameters. And how we can calculate the expectation value corresponding to this psi QSE state, it is like, so we just simply calculate the expectation value for some observable O. And what we obtain is like, this is a classical parameter, sorry, we need to also have the I prime here. And by calculating the matrix representation of the observable in this basis, psi I basis, and we measure this on quantum computer. Yeah, there are a lot of ways to compute such kind of overlap metrics. And by calculating this on the quantum computer, and what we need to do is like by applying the classical parameter, and we can just sum up. Graphically, we can understand this way, this procedure in this way. So first, we calculate the overlap matrix. This one on quantum computer, this green shaded area. And once we measure this on quantum computer, this is just a classical metrics. So and these are just a classical metrics, so we can just perform the calculation on the classical computer, and finally we can compute the expectation value corresponding to this classical quantum ansatz. And the optimization of this classical parameter C can be done by solving generalized eigenvalue problem based on the result from quantum computers. I do not detail this method today due to the limitation of time, but if you are interested, I can explain about that. And I develop this method to simulate the larger quantum systems, and this is called hybrid tensor network. And I'd like to introduce a preliminary example. So suppose we only have the 100 qubit processor A and B. So the number of the qubit is not free scalable. So suppose that we just have the 100 qubit systems. And even when these are just separable systems, the superposition linear combination of these separable systems forms the entanglement state corresponding to 200 qubit wave function. So this is composite system A plus B, as I introduced. And we also measure the expectation value corresponding to this wave function, and in the similar way. And what we obtain is like we have the overlap matrix for subsystem A and subsystem B, and once we obtain the we calculate this on quantum computer A and B, and once we compute these values, these are just classical matrix, and again we can just compute this on classical computers, and finally we can simulate the entangled system with a hybrid way. And actually we can further develop this method. Like we can increase the number of the subsystems more than 2 in this way. So n is the number of the subsystems, and we can further replace this classical parameter with quantum amplitudes. The calculation procedure is in this way. So as in the previous example, we can again compute the this M overlap matrix in quantum computers, and we obtain M matrix, and this is the same. So we do this for n separate subsystems independently, and we obtain M1, M2, M matrix. And actually, we can easily show that these metrics matrices are just Hermite matrices, which mean these are observables. So this is just a tensor product of observables. So we can easily compute the expectation value of the observable by simple diagonalization. And so yeah, we measure the expectation value for this quantum state psi. Psi is represented in this way, and we can compute the expectation value for this observable. And suppose that each subsystem composed of k qubits, and if we have n subsystems, this corresponds to the nk qubit system simulation, which allows us a tremendously large quantum system simulation. Okay, and actually, we formulated the other types of the divide and conquer techniques under the framework of the hybrid tensor network. This is our accomplishment. And yeah, so for example, entanglement forging and deep BQE is also very appealing divide and conquer techniques, but can be formulated under the hybrid tensor framework. Okay, and we proceed to our accomplishments. Actually, in the previous example of the hybrid tensor networks, only the expectation value of observable can be computed, but sometimes we are also interested in the transition amplitude as well. For example, calculation of the Green's function, which is useful for material science, and also calculation of the overlaps between two states, useful for many algorithms. For example, excited state evaluation, machine learning, and so on. And okay, and the different thing with the previous examples are like for calculation of the transition amplitude, we have different quantum state, psi and phi. So actually the contracted matrix, so like I denoted as M, becomes a non-Hermite matrix N due to the difference of the quantum states. And actually, non-Hermite matrices NK appear during contractions, and the contraction rules proposed in the previous work cannot be used. So, so we developed this. And one way to compute this value for non-Hermite matrices n is like we can just decompose this non-Hermite matrices as a linear combination of the Pauli operators, but the number of terms increases exponentially with the number of subsystem n when we use a naive technique. And yeah, we propose to use singular value decomposition for the non-Hermite matrix. So actually, this is just a 2x2 matrix. When the bond dimension is 2, we can easily apply singular value decomposition for this non-Hermite matrix. So this B is and C are the unitaries, and this is a diagonal matrix with positive entries. And by using the following Adamant test-like circuit, we can calculate this transition amplitude. This is an ancillary qubit, which determines whether we compute the real part or imaginary part of the transition amplitude. And this quantum circuit generates quantum state psi, and this UM2 generates phi. And yeah, these unitary operators correspond to the singular value decomposition unitary operators. And we assign the singular values as outcome to the measurement outcomes. In this way, we can compute the transition amplitude corresponding to the non-Hermite matrices. And we show that the number of the measurement to assure the required accuracy scaled as the product of the singular values of the non-Hermite matrices. And we checked that the singular value is less than 1, typically by a numerical simulation in usual cases, and there is not generally exponential sampling overhead in the number of subsystem n. Okay, and we also proceed to the noise analysis in the hybrid tensor networks. As you know, we have noise in quantum computers, so we need to consider the noise effect in calculation, and we consider the stochastic noise like T1 errors and T2 errors and depolarizing noise, and we do not consider short noise in this stage in this study. And to do this, we introduced the expansion operators. So original representation of the hybrid tensor network is like this way. So this amplitude is generated by the quantum computers, and we have the N subsystems, which is also composed of the large quantum computers. And we introduced an expansion operator. This is like, so this expansion operator AK converts the qubit 0 and 1, transforms a large quantum state, psi ik. And by applying this expansion operator to the quantum state psi, we can obtain the hybrid tensor network state. And so our concern is about noise in the hybrid tensor network. So we needed to think about the density metrics. And actually, by using this one, we can represent the density matrix representation of the hybrid tensor state in this way. This super operator is defined as this one. And actually, we show that under the effect of noise, this expansion super operator also transforms to the CPTP map super operator in the dominant class of the quantum state preparation methods. And by using this, we can systematically discuss the effect of the noise propagation and expansion of the simulated system in hybrid tensor networks. So we start from the parent tensor, and by applying the noisy expansion operators, we can systematically define the noisy hybrid tensor network state. And in many cases, in dominant case, the expansion operators are CPTP map. So we can also check that resulting hybrid tensor network state is also positive semi-infinite operator, which guarantees the application of VQE or other variation algorithms. And also, we consider the specific type of noise, global depolarizing noise, for each quantum tensor. And in this case, the noisy expansion super operator becomes in this way. P is the failure probability of computation, and we get this one. And by applying these noisy expansion operators sequentially, and actually we have the product of the success probability in this way. So this indicates that exponential decay of the observable with a number of used quantum tensors is observed. And we also verify this in numerical simulations. And this means that actually the expectation value shrinks exponentially with the number of the used quantum tensors. So balancing the number of quantum tensors and classical tensors is very important in this hybrid computation. Okay, I'll proceed to the error mitigation, developing the quantum subspace expansion. In quantum subspace expansion, again, we apply the kind of the projector-like operator decomposed by linear combination of power operator in this way. And we apply this, and we try to minimize the energy as much as possible. And actually, this is formulated for pure states. And actually, it was checked that it's good for coherent errors like rotation and also the insufficiency of the answers of the variational quantum eigensolver or such kind of thing. But it was also it's also known that this technique is almost useless for stochastic errors such as T1 and T2 errors. And to overcome this problem, we propose a generalized quantum subspace expansion technique. I introduced an example of the power subspace method. Actually, this is very general framework, but I just explained a specific example. And by decomposing this projector-like operator by power operators, we also expand this projector-like operator also with quantum state itself. And we apply this projector-like operator P tilde to noisy state psi. And what do we obtain after we apply this operator is like we can have the series expansion of the powers of the quantum states. And due to this power freedom, we can also mitigate stochastic errors as well. So we can also mitigate coherent errors and stochastic errors, and we can realize a very general quantum ansatz in hybrid quantum simulation. But there is a kind of overhead, large overhead. Actually, this method is based on virtual distillation and exponential separation technique. And this technique uses copies of the quantum states to calculate the power freedom of the quantum states. So this is a large overhead for current quantum computer where the scalability is limited. But recently, computation of the power of the quantum state without copies of states, but requiring the doubled depth is proposed. This is called dual state verification. This is kind of the conversion of the space cost with the time cost. And actually, this does not require the copies of the quantum states, so much more hardware efficient. And actually, so by incorporating this, we propose a dual GSE framework, and also we further incorporated the divide and conquer strategy of the hybrid tensor network in our framework, and we propose a framework. We can simulate a larger quantum system as well as mitigating the effect of noise. So this is a schematic. So the original GSE, generalized quantum subspace expansion, was copies of the quantum states. So the number of the qubit is doubled. But by using the dual, we can make the number of the qubit half. And by using the divide and conquer strategy, we can even more reduce the number of the qubits. So, and the number of qubit count is reduced 4 times with the original GSE framework. And we did some numerical simulation. This M implies, so the horizontal axis M implies the representability of broad class of quantum states, and how powerful the understate is. And this delta E is the difference from the ideal quantum states. And this line corresponds to the without divide and conquer strategy, like separable answers. And we simulated the 3 error rate regime. And we checked that as we increase the ansatz representability, we can systematically reduce the difference of errors. So, implying the entanglement is introduced classically, as well as mitigating errors as well. And another resource efficient advantage of this method is like we can make the count of the qubit system half, so the possible number of combination of Pauli string is reduced to 4n to 2 from 4 to n. So this also offers a hardware-friendly strategy, even from the measurement as well. And this is the conclusion. Quantum subspace expansion is a basic hybrid quantum classical algorithms, which evolved into divide and conquer methods and high-performance quantum error mitigation. And the hybrid tensor network is a general framework that can describe many divide and conquer scenarios. And we propose a method to compute the transition amplitude and give a framework for noisy hybrid tensor networks. For noise problems, in many cases, the simulated state is physical, positive semi-definite, but we need to be careful about the exponential decay of the observable with the number of the quantum tensors. So balancing the number of classical and quantum tensors is very important. And we propose a generalized quantum subspace expansion technique, which can suppress both coherent and stochastic errors due to the power freedom of the state. And we further propose a resource-efficient GSE framework using dual state verification, and even further incorporates the divide and conquer framework, which makes error mitigation much more hardware-friendly. And outlook is like we can further unify the GSE with the hybrid tensor network, maybe. And application to early error-corrected quantum computer is also a very interesting topic. Thank you very much.